So I didn't intend to give a talk, but I'll just thank you. Okay, so value categories is something in C++. I mean, it's chill. You guys can just ask questions anytime. Don't make it too formal, please. Okay, so yes, basically this is a list of stuff I probably will go through. So I plan to motivate. Hello. Hi. I plan to go through like value categories from the ground up. So like imagine you know nothing about C++ right now. Okay, so in the very beginning, we had C, right? And in order, if you want a function to modify something, you pass a pointer into the function, right? And then the function will dereference the pointer, and then the function will dereference the pointer and play with it. So this was annoying for two main reasons. One was that if you pass in a pointer, everywhere you have a pointer, you always whenever you want to dereference something, you always need to check whether it's null. Because if you dereference null pointer, that's very bad. So another thing was that this was kind of ugly for like operator overloading when you kind of the whole idea was that C wanted people to treat class type objects as the same thing as like primitive type objects where you have X++, right? They wanted to have like a month plus plus, like where you can do a plus plus to a class kind of stuff. So they wanted basically you to define when you define a class, it's not like class type and like primitive type separate. They wanted the semantics to be kind of similar. So they wanted operator overloading. So the solution in C++98 was to have references. So under the hood, references is still pointers, right? Under the hood, like everything you can do with references, you can replicate with pointers. It's just that the language semantics makes it such that references are like there's some checks here and there. So now references give you a way to pass in the object, and now you can use let's say I have a reference to month denoted by month ampersand here m. Now whenever I have access month, right, it's as if right I had a pointer to the month and then I dereference it. So now imagine like this month ampersand m is effectively the same thing as a month star m, and then everywhere I see a m, I put a dereference m. So basically this allow you to kind of use pointers without number one, without needing to check whether it's null pointer, because you can never pass in a reference to null. And number two, you can now you can do operator loading a bit more conveniently. Yeah, so the benefits to this the benefits of references are basically the same thing as benefits of pointers, right? In that you don't need to make a copy of all the data, you can pass a pointer to it, and then yeah, it's cheaper to pass things into functions. Yeah. So okay, so under the hood is still a pointer, right? Which means that now C++98 has references, but what are the problems with it? One problem is that you cannot pass in, if let's say I have a function 1 that takes in a reference to int, I cannot pass in a constant 10 because if the reference is under the hood is a pointer, you don't have a pointer to 10, right? There's no such thing as, hello. You have no such thing as a pointer to 10 because 10 is a constant. When you compile the assembly, it's like move something 10, like literally is if you learn the assembly instructions, it's an immediate type, right?
So you're saying it will compile, or like there will be a compilation error?
There'll be an error. So this will be compilation error.
Okay.
Yeah. So that's the problem with references right now. Yeah. So how do we fix that? Okay. So before that, right? I won't go to the solution yet, but let me just introduce some terminology along the way. So in this case, how do we formally describe this problem? To formally describe this problem, we say that whenever I have a variable in some sense, this variable is a L value. And whenever I have a constant here, this constant is kind of like an R value. We call it R value. Roughly speaking, L values appear on left hand side of variables of equal signs, and R values appear on right hand side of equal signs. So like let's say in this case A equals to 5, A is a L value, then equals then the R value here is 5 is the R value. So that's roughly speaking, but that definition doesn't hold exactly true. So the exact definition, the more precise definition is that L values correspond to variables that have some location. So they live in some they have some address, right? Either on the stack or the heap. And R values are things that are not L values. So basically, it's a bit funny that they find it this way, but this turns out to be a theme in C++ value categories. So now, yeah? yeah. So now we call that thing. So now we call that int ampersand x thing and L. We call that thing an L value reference to int. And yeah. So L value reference. This term is a reference to L value, but I'll actually hold on this definition. Like I'll say that this definition causes more confusion because later on when we define things like constant L value references, they can be references to this definition doesn't really make sense later. So I prefer to define L value reference as something that tells the function one that this x is something they can modify. Okay, so now parameters, they have certain type like that, right? When you have a function and one of the function is int ampersand, that L value reference tells the function that this function can modify x. Okay, and it will affect the caller. Whenever the caller passed in, right, that function can modify it. So I like to think of L value references and later on R value references as things that are basically telling the function what the function can do with the data. Okay, so now this error over here, now it makes sense because now this R value doesn't have a address, right? It doesn't have a location in either the stack or the heap. This 10 over here is a constant. It does not have an address. And from the point, so there's two perspectives to understand this error. One perspective is that references work with pointers, and there's no pointer to 10, right? That's one perspective. But that's like the C kind of perspective, like the C way of understanding it. But the C++ way of understanding it is that this R value cannot bind to the L value reference. So that's a sentence that this kind of lingo is stuff that we'll get used to, right? We say that a certain L value or certain value category cannot bind to a certain reference type. Yeah. So now we understand this error in the following ways. So what's the solution to this? The solution is for C++ to introduce const L value references. So now I have a function 2 that is const int ampersand. And what that means is that it's a reference to a constant integer. So that's what we call a constant L value reference. And this basically, when I have a parameter that is a constant L value reference, it tells the function 2 that function 2 cannot modify the contents of x. So it can read the contents of x, but it cannot modify it, right? And yeah, so if I go back a little bit, just now over here I said that I don't like this reference, right? Because L value reference is a reference to L value. It's not a very useful definition. Instead, I like to think of L value reference as telling the function it can modify it. This definition works better because it now contrasts with constant L value reference because it tells the function it cannot modify it. So now basically the L value reference or constant L value reference tells you whether the function can modify it or not, right? Yeah. So now if I call function 1, I pass in A, this is okay. If I pass it A into function 2, it's also okay, right? Because function 2 doesn't modify A, it's fine. But previously we had an error when we tried to pass an R value in function 1, right? Because function 1 is saying that I can potentially modify x, but this is a constant, so I can't modify this value. Whereas function 2, the semantics of function 2 is saying that function 2 will only read the value of x. It will not modify it because of this const int ampersand here, right? And so that's why this binding is okay. So this is this tree 1, 2, and 4, lines 1, 2, and 4, this compile just fine, but line 3 doesn't compile. Yeah, so now passing in a normal variable to function 2 is okay, because it simply means that I pass in the variable, the function doesn't change it. But passing in the constant is now also okay, right? The function 2.
Okay. So what does the compiler do want to put? Like, does it push a value onto the stack with the value 10 and then does it basically define a new variable?
No. So in this case, because it's references, right? References, if you put in the godboard and the decompiler, you see that references compile down to pointers. So under the hood, for now. So under the hood, we pass in this A, is passing the pointer to A, and it's passing a pointer to A.
Okay.
Yeah, so is it creating a new variable and then like with the value 10 and then passing the pointer?
Is it like storing?
Oh, for this one, is it?
Yeah.
Storing 10 into a register and then
Okay, so Is it?
Okay, so it's essentially right, C++, right, it doesn't define exactly how you can do it. So references, right, just defines that it's a, you can think of it as a non-null pointer, but it's not necessarily a pointer. It's possible for the compiler, right, to completely optimize the way such that it doesn't even, such that there's no pointer at all. It can do anything
it's
it
not
wants
necessary.
as long as that the way it acts, right, is according to the spec.
I see. Oh, so
So-
yeah.
You can think of it as, yeah, sure. If you want to simplify things, sure. Yeah, it pushes on the stack and passes a pointer to the stack. But it's not necessary that it does.
Yeah. So the specs doesn't say anything about how the compiler should do it.
So there's an optimization where the pushing up the stack is not necessary. It could just like
So like, yeah, for example, in this case, let's say fun 2, right, if you just return
Return
a thing, right?
Yeah.
Then you can completely optimize the way fun 2. Then you don't need to store it on the stack even, right?
that's true.
Mostly when you call stuff with constant values, like in X64-bit architecture, like it's stored in your register, right? You won't even be on the stack.
Oh, right.
Your first few arguments.
Right, that's true. So yeah, right. I think like the first few, if you pass in a very little number of arguments, usually they use the registers. Yeah. So yeah, so the semantics of language is this, but the way the assembly exactly looks is could differ. Okay, so with this example, right, we can summarize in a nice table where we have this thing called reference binding. So okay, so we saw constant L value reference, which basically, if you have a constant L value reference parameter, okay, if you have a constant L value reference as a parameter, it tells the function that this function, it tells, there's two things it tells. It tells the function, the person who implements the function, that I cannot change the contents of it. Otherwise, the compiler will complain, right? And number two, it tells the caller that this function will never change your parameter. So whenever you see a parameter type, right, like constant L value reference or L value reference, it always tells the two parties, one is the function implementer and one is the caller. Essentially the contract, the agreement that this function would not alter the parameter for the constant L value reference. So whenever you have a parameter type like that, it's like intermediating a contract between the caller and the function. It's like, yeah. So that's the way I like to think about it. And this idea that the type, right, the reference type kind of negotiates this contract between the caller and the function. This idea kind of carries over to move semantics later also, where you have more complicated reference types. So we have two types right now, two reference types right now, L value reference and constant L value reference. And the bindings are as such. So L value, for now, you can roughly think about it like a variable that has a address or location. And in this case, it binds to both, right? Because a function that it binds to both. And then, okay, so note the difference between an L value expression and a reference type. Namely, the column over here, the rows over here, this reference type tell you what the function might do, right? It tells you what the function might do to the parameter. And those up there tells you what expression, those up there correspond to what expressions you pass in. So L value roughly corresponds to a variable. If you pass in a variable to a function, you can pass in a variable to either something that might change it or something that will not change it, right? Then if you pass in a constant variable into a function, right, you cannot pass it into a function that might change it, right? Because otherwise it breaks the contract, right? But you can pass it into a function that would only read it, will not change it. So that makes this second column make sense. And lastly, over here, R value is basically, it doesn't have it's kind of like a constant, right? Like a literal, like 10 or like a x plus 1. It's kind of like a literal that it's not a variable. So you can only pass it, you cannot pass it to a function that changes it, because it is kind of like a constant. Whereas you can pass it to a function that only reads it. It doesn't modify it. So that's how this table works. Right? So this table will be expanded later when we include move semantics also.
Can you elaborate on data that don't implement? What kind of data does it
Wait, let me see. L value.
implement? Are you referring to R values?
So it can't bind to, yeah. But by this line I mean R values.
Okay.
R values don't live in memory, as in how is it?
like they don't have a address location. Wait, this line is not very. I can just say R values here. Like I made this slides a bit. I should have deleted the line and said just R values. I should have just deleted the line and said R values.
Oh, I see. Like, you say memory.
Yeah, like memory. Okay, so with that we actually understood references in 1998. So C++11, the main changes were that they wanted to introduce something called move semantics. So I spent a lot of some time going through what move semantics is right now. The real way to get good at move semantics is to practice with Rust, because the Rust is a compiler that would use a baton and whack you whenever you violate move semantics. So the best way is really to code something in Rust, but I'll try to go through like the rough ideas for now. So this C++11 expands the table to something a bit bigger that looks like a horse. But don't worry about it. We'll kind of motivate this entire table. Okay, so this is also the full value category. Instead of just L value and R value, they expanded to all these BS. But we can take it step by step. It will make sense later. Okay, so first, let's introduce a ownership model. So we know that in Java there's a garbage collection, right, where you allocate things on a heap and you don't really need the thing anymore. The garbage collector will come and free it up for you. And it's something that runs in the background. Hey, hello. Come in. Yeah, let's join. So in Java there's a garbage collector, but in C++ there's no garbage collector. So we need a better way to manage memory. So the main idea behind ownership model. Okay, so this is my interpretation of this is my intuition about it. Might not be fully precise. You can feel free to nitpick. But this is my intuition. So so feel free to voice the concerns. So the idea is that every object in the ownership model should have an owner, and that owner is either another object or a scope, right? And I say should have because you should follow this rule, but if you violate this rule by allocating something on a heap and not having something own it, then you have something like memory leak later. So this should have is more like, it's not something the compiler enforces, but it's a guideline that you should follow. Rust will try to enforce it, but C++ lets you play with around and shoot yourself in the foot. So this is a rough rule. So let's say I have a struct cat over here. There's an int age, food f, and toy reference. A reference to toy t. In this case, we say that the cat has ownership of the int age. Although usually we don't really care about primitive variables. We usually care more about like objects owning objects. So we in this case we say that cat has ownership of the two variables the two fields that it contains basically. And we don't say that it owns toy because it only holds a reference to it. Maybe some other person owns toy, but cat doesn't own toy, right? So the rule here is that every object has an owner, and in this case, objects can own objects. This is an example of it. Okay, then the next thing, an object can have a scope as an owner. So let's say in main, right? It could be in main or it could be in a for loop or something. But let's say in one of the scopes, I have a cat C like that in this case. Then we say that the C's owner is the scope. Is this curly brackets the scope? And so if you trace this out, right? You trace this out. Okay, so before we talk about the tree, an object when it's destroyed, an object is destroyed when its owner calls its destructor, right? And usually the owner will call its destructor in two cases, right? Because the owner can either be an object or a scope. If the owner is another object, usually the owner calls its destructor. Usually the owner calls its destructor when the owner itself is destroyed. And if the owner is a scope, then it calls its destructor when it basically exit the scope.
Is it possible for a thing that is owned to have its destructor called before the owner's destructor gets called?
Yes. So as in you should design a program such that does not happen.
Okay.
Right? Because if not, the owner would be like, hey, where did my child go? Right? Yeah. So you should design a program such that it does not happen. But C++ lets you do a lot of things. And that's one of the things that it allows you to do, but it'll be quite dangerous and not easily it's not good code.
Wait, why is it dangerous? Like, if you cause an error in no idea.
yeah, so like let's say I'm a parent, and then let's say I'm a cat and I have a food, right? And then let's say somebody else who has reference to the food goes and destroy it. Then as a cat, if I try to access the food like f.eat or something, then I might have it'll be bad, yeah.
You're looking at ground.
So with that in mind, when an object has a owner that's either another object or a scope, that leads itself to a very natural tree structure of ownership, right? Because each guy only has so that leads itself to a very natural tree of ownership where the nodes are objects, edges are ownership, like so the parent owns a child. Leaves are primitive types, right? So your leaves are always like integers or floats and all that, primitive types, and your non-leaves are your class types, roughly speaking, right? And then the roots of them, because you go up, eventually you reach a root, right? And the root will be a scope. And so if you think about it, is a program will have many trees in its lifetime. So let's say a program is running, you create one tree here, one tree of ownership, one tree of ownership. Then these trees will come in and out of existence, right? When I create a new object, I create a new node, and new nodes and stuff, and trees are deleted when the scope goes out. Okay, so like when the scope goes out and the root gets destroyed, then entire tree propagates down the destructors.
But it's possible for one tree to like have an edge that connects to a different tree.
One tree to have a no because
But
no,
let's say
because
I pass an object.
okay, actually yes, you can. We call that like shared ownership kind of, and you can have stuff where so let's say you want to model a deck, right? Model like a graph. Then it kind of natural to have like one node to have like multiple parents. But in those cases, you usually have like shared pointer to like handle this kind of references and like reference counting to make sure that you don't free yourself before all your parents like
I did.
yeah before all your parents like disown you.
Yeah.
So yeah, you can have shared ownership, but for now let's just stick to trees.
Okay.
Yeah. Okay, so I have an example over here where so this is an example of the tree structure. So I have if you look at the code over here. Okay, so in this case, I have a toy, I have a food. So basically, all these destructors and constructors are simply just all these constructors and destructors are simply just I just annotated them with C out so I can see when something is constructed or destructed. So I have a toy, I have a food, I have a dog, and now I have a cat that owns a toy, it owns a food, and it's a reference to a dog. And so now I have a human that owns a cat. And now in the main function, I create a human H. And so if we trace the program output, right, you see that when you create a human H, it first creates a toy, right? It first creates a toy constructor, then it creates a food, then it creates a dog, then it creates a cat. And so you can see it's kind of like a post order, right? Because the tree structure is human, cat, food, toy. And the creation is kind of like post order traversal on this tree, right? Where I have a toy, food, cat, human. And yeah, and you see, okay, so you constructed a dog also, construct a human. And now when I reach line 61 where the end of scope is approaching, then the human gets destructed. And then the human calls the destructors on all the child that it owns. So it calls the destructor on the cat also. And the cat now calls the destructor on all the children, all the things they own, which is food and toy. But notice that the cat does not call the destructor on dog. And the reason is because over here is a reference to dog. It doesn't own the dog. It only has a reference to the dog in line 35. Okay? So you can see in this case, actually this program demonstrates a memory leak over here. Because the dog is created when I create a cat, but the dog is not destroyed when I destroy the cat. Right?
Yes.
Yeah. So in this case, in this example, you can play the God link yourself, but in this case, the dog has no owner, because it lives on a heap, which is also a good thing because it doesn't get destroyed. Right. So that's a memory leak.
Sorry, why does it need?
Okay, sorry. It's not a good thing. It's not a good thing.
Why does the computer set?
Oh, the dog lives on a heap because it's allocated using new. yeah.
Okay.
Yeah, it's allocated using new. That's why.
So if owner is like anonymous.
So it has no owner. The dog is a stray dog.
So you're gonna disrupt it. Okay.
If you don't, because the only place I ever store a pointer to dog is in the cat, right?
Right.
Yeah. So if the cat code doesn't have like dog playmate dog, like, if it doesn't have something like that, then it will never. Does this work? No, this doesn't. Yeah, this works. So if it doesn't, this is how you destroy it. If you want to, so if you write code and you don't want a memory leak, you need something like line 42 where you in the destructor of cat, because you especially have because you kind of did some manual allocation here, you need to do some manual deletion here.
Right.
So that's actually something like the rule of three, where if I kind of like manage my own resource, then I must take care of my own resource when I deal with details.
Right, but ownership model is like we don't want to do this.
Yeah, the ownership model says that we don't really want to do this, and if we do it, we want to do it correctly also. Okay, so yeah,
If
so
you're not doing, if you're letting the compiler do automatically, then isn't everything on the stack? Because if it's on the heap, then like you're not actually owning it, right?
There are ways to, maybe you can weigh in, but maybe you guys can weigh in, but if you're allocating something on a heap, you can create like a smart pointer to it, so you don't really do the manual allocation and deallocation yourself, but you let the smart pointer wrapper kind of handle it.
Okay.
Do you guys have anything?
So one example, right, is like vectors, right? You know C++ has vectors.
Yes.
So see, the way you implement C++ vectors is you allocate an array on heap. But the C++ vector struct on stack is the owner of the array that's on the heap. So yes, it can be on the heap, but it still has to be
Okay.
which is the struct on stack.
Do we answer your
Yeah.
question? Okay, so that's great and all. So now you know that there's a tree of ownership and all that. But what's good about that if you cannot transfer ownership to other stuff? So it's like we the whole idea of move semantics is we want to move ownership from one. We want to move like one tree into a subtree of another guy or something like that, right? So we want to transfer ownership to other owners. So to do so. So the way that C++ does this, and this is a design decision, right? They could have, Rust does it a bit differently, but the way that C++ chose to do this is that the function must have this cat ampersand C to indicate that C is ready to be moved into the function f. Or rather, the f can take ownership of the C. So this is what we call an R value reference. And so now we have three kind of semantics over here where I have a function g here that takes a cat, and if I pass a cat into it, it actually makes a copy of the cat and pass into it.
Right.
And then now if I have a if I f here that is a reference to cat, L value reference to cat, then when I pass in the C, we say that f in this case borrows a cat because it borrows a cat, it in the function f over here can modify the cat, but eventually the function f here does not take ownership of the cat, right? The function here f eventually returns the ownership back to the caller. And so that's what we call borrowing, right? This function borrows the cat for a short while, and after the function exits, remember functions are scopes also, right? There's a scope here, and that means that within the scope, the borrowed cat over here is only borrowed from its caller. It's not, it cannot take ownership of it, right? So yeah. So that's borrowing, where I pass a cat into the function, and then eventually the function returns me the ownership. And C++ 11 adds the move semantics where I can have a cat ampersand here, and this is called an R value reference to cat. And in this case, if I do like something that's move C, I'll talk more about this later. But so if I do something like that, then it actually moves ownership of this cat C into the function f, into the scope. Right? So now the owner of cat becomes the scope of the function.
Wait, so what happens to the original owner of the cat? Does he lose ownership?
Yes, he loses ownership, meaning that if I stood move on C, after this line, I cannot touch C ever again. Right? I've lost ownership of the cat in this function, in this scope.
So it becomes like a disrupted value.
We don't call it destructed because the cat has not died. It just transferred to another owner.
So what happens if I try to access C now? We just
Undefined behavior. So your cat can get pregnant.
Oh.
That's actually like a line that they say, like, apparently, like, I hear one of the talks, right? They were like, there's one instance where undefined behavior caused a guy's monitor to catch fire. Like, when we hit undefined behavior in C++, right, anything can happen. Like, the compiler is like anything can happen. Like, you can form a wormhole or something, like just everything goes bombarded. So, yeah, touching C after it's been moved is undefined behavior. After it's been marked moved is undefined behavior. So, yeah, so these are reference binding rules for C++11, but thankfully, the const R value and const R value reference is not so important. There's very few nuances with regard to it. So actually, we only need to focus on this subtable. Actually, 6 out of 9 of these we already completed, right? We already understood them. So we only need to understand the remaining 3 squares. So remember just now that I said that ref and the L value ref and const L value ref refers, it means that the function cannot take ownership of me, right? It tells a function that, yeah, it tells a function, in this case, the first one over here tells the function you can modify me, the second one here tells you that you can read me, but either of these case, the function cannot take ownership of the thing that you pass in. This is contrast with the R value reference, where the function is told that it can take ownership of whatever you pass in. So that's what the R value reference is, and this new column is what's introduced in C++11. So we already understood this square, right? A quick recap is that L value is basically a variable, kind of, and L value you can pass into a function that either modifies it or does not modify it, right? Just reads. If you have a constant variable, you can only pass it into a function that only reads it. You cannot pass a constant variable into something that modifies it. And R value is something that's kind of like a constant neutral that you can only pass into a function that reads it, but not something that modifies it. Right? So these 6 squares were understood previously.
So, I can pass the constant 10 into a function that takes in
that takes ownership.
Yeah.
Yes. Yeah.
Wait, so can I clarify this? So basically, the situation in which we want to use this ownership moving is when we want only R values to be passed into a function.
Okay. If I step back a bit, the whole ownership model thing is a way of managing memory.
Right.
Like, it's an alternative to garbage collection.
Yeah,
So-
it's like you manage the memory yourself. Right?
Yeah.
So wait, so as in this instance, because if we pass in a non-R value into a double n%, then we create undefined behavior, which is not what we want in any code, right? So
Wait,
it
when-
means that
Sorry, when you say I pass in a non-R value,
yeah, like let's say we pass in
A variable, right?
yeah, we pass in a variable, then then the cat, like let's say that cat
Oh.
for example.
so you're saying what if I pass a variable like L value into this one, is it?
Yeah.
Oh, it does not bind. The compiler will not bind it for you.
Oh, okay.
So that means if I try to pass in, the compiler will say like you cannot pass that into this.
Oh.
Yeah. So the ticks are the cases where the variable, the expression you pass in the function, or the expression you pass in the function can be bound to the parameters. And the numbers here are priorities. So like if let's say I pass in an R value into some function, let's say I have 3 overloads. Okay, that doesn't really. Let's say there's a hidden column here, but this is first and second. So these are priorities. So let's say I have a function that takes an L value reference, and the function also takes in a constant L value reference. If I try to pass in an L value, it will first bind to this if that exists. If this function does not exist, then it will bind to this function.
Right. Okay. So basically, we use this when we want to say pass in something that the function scope will take ownership of, so that it can be cleared once the function exits.
You're saying the n is it?
Yeah.
Yeah, correct. So
okay.
n tells the function that you can take ownership of what I pass in.
So that
But how does it look like in memory when you're taking ownership? Because like example, you pass in a constant 10, right? Like this will be like either push to the stack or put in the register. So when I transfer ownership to the sub function, right? Is it like a copy is made and then put in that function scope of memory? Or like it's a pointer back somewhere, but that's kind of weird as well.
So you're saying when I pass in 10 into f %, what does it look like in terms of the stack, is it?
Yeah, correct.
I think just like what Zeno said just now is these are the spec just indicate the semantics of the language. It doesn't enforce how the compiler does it in assembly.
So this is also based on compiler.
Yeah.
But then the semantics says it takes ownership, right?
Mm.
So what does it mean to take ownership of the constant n?
Yeah, you remember the tree?
Just the tree.
Yeah, so
For constant then it's not a very good example because like a constant by itself, right? It's really it's like it's literally called a trivial type. So like let's ignore it. So like for example, if you do something else,
I don't know what it's called.
like
Let's see.
another struct, right? If you return a struct from a function, then that becomes an R value. It's an R value because you return it from a function. So what you can now do is that if you return the struct from a function and then you pass it into a function that accepts %, right? Now within that new function, it can take ownership of that, which means it can move the contents of the you explain what I think you explain it later, right? So you can move the contents of the R value and take ownership of it, whatever that is. So it doesn't really copy it, but it really just take over the value in some sense. Yeah.
I think for now, your mental model can be, remember the tree of ownership, right?
Yeah.
If you make a copy, you duplicate the node, right? But if you move, you delete an edge and then you draw a new edge.
Okay.
Actually, that's quite, I think that's a,
And then if it's a constant, just ignore it.
if it's a
That's
cons,
better.
yeah, kind of, it's a leaf node, so it kind of, yeah, doesn't really matter.
Wait, what's the primitives, right? No, wait, so what do you mean by
Like-
it can only be a leaf node?
like your primitive types are kind of like leaf nodes in the ownership tree.
Yeah, I said primitive types of leaf node. So okay, then how about you guys continue first?
So in this case, we understood this. So how do we understand the remaining three squares? I'll understand it. We can form understanding of it by understanding it as a design choice. Like when you introduced C++11, right? Nobody really said that you need to have these three squares like that, right? But it's a design choice the people made that say like, oh, these three squares will be as such. In this case, the design choice we make is that L values, right? L value or constant L value expressions, they cannot be moved. So in this case, because they cannot be moved, I cannot pass it into a function that will possibly move them, right? Because that's what this double ampersand means. This double ampersand as a reference type in the parameter of the function, this double ampersand, f ampersand means that the function f could move whenever I pass in. In this case, that explains why the L values cannot bind to this double ampersand. Right? So it's a design choice. I say that I make L values the things that cannot be moved. Okay? And then R value means it can be moved. So this three squares is also explained. Right? So every expression in C++ can either be moved or not moved, right? This is law of excluded middle, right? So it's either L value or R value. So this
Can it be both?
no. Yeah, I don't think so. Right? Yeah, so okay, this line is definitely true. Every expression is either L value or R value. Later I'll show you the tree. But this line is my intuition for why this is true, because based on the definition of L value and R value, yeah. So now we can define new value categories. So previously we had L value, R value. Now we have a lot more things, right? So previously we had R value and L value, right? Now they're here. And now we introduce these new guys. And so it looks complicated, but let's try to motivate it from scratch. Okay, so we invented R value references to indicate that functions can take ownership of the parameters they pass in, right? But right now, the only things they can pass in, the only thing that can bind to double ampersand is the R value, which means that the only thing you can pass into functions that take ownership of stuff are constants, which defeats the whole point, right? Because now I'm saying that in the ownership tree, like only leaf nodes can be moved around, right? But we want the ownership model. The ownership model, we want to be more flexible. We want to move entire subtrees, right? We don't just want to move the leaf nodes.
Wait,
So-
in this current model, you can't move a subtree into the thing. How does that question work?
As in, because right now the only, before I mentioned X values, right? R values are the only R values out there right now that we know of is like constants, like literals.
We can't pass in something like new cow, for example, as a constant. Is it? It's not really.
I'll get to that. New cow is actually a PR value. So, I'll get to that. But right now I'm just saying that under the current what we know, right? What we know from this so far, what we know is that R values are like literals, and that means that this model of ownership is kind of useless, right? Because I can only like move literals, like I can only move around the leaf nodes, but I want something more flexible than that. So that's why we need to invent new value categories and new ways to describe how to move entire trees. So the way to solve this is that we make a new design choice, which is that I can convert an L value to an R value. So remember, L value are like roughly speaking variables, right? And they can represent entire subtrees, entire trees of ownership. And so now if I invent a way to convert the entire tree into something that is an R value, then I can move entire trees. I can move entire trees into children of other nodes. I can move like I can this is a full ownership model, right? So I need a way to convert L value to R value, and this is a design choice that the language creators made. And the way to do so is to mark it with std move. So std move will convert an L value to an R value. And how they do so under the hood, not very important, but it's quite simple also. It's not, so I won't delve too much on it, but this is how they convert it. And so there's this very nice description of it. I took a screenshot, and what they say is that what is std move, right? Std move is technically a function. It takes in the input and gives you an output, but it's really more of a, it's not a function that like manipulates the data in any way or even a type. Yeah, moreover, it is a converter that kind of converts one expression's value category to another value category. And basically what it means is just that whenever I pass it into std move, if it's an R value, then the std move will return an R value. If it's a L value, I pass in an L value, then the std move will return an R value also. So whenever I pass in the std move, comes out an R value. So right, so it's something that just eats everything and turns in and poops out an R value. So that's what the std move does, right? And note that it doesn't actually move anything. It just changes the value category semantics of the expression, right? And what actually does the moving is the function that you pass it into, right? So remember that. Oh, bye. No worries, bye. So what actually does the moving is the function, right? The function, if it's marked as double ampersand, that function is the thing that can move the contents of the parameters to another owner. So yeah, so this is what std move does. It doesn't, you always hear this, if you watch all the talks, they always keep on saying that std move doesn't actually move anything. It just marks the thing as an R value, and when you pass an R value to a function, then that function would possibly move it. So std move, put std move an L value, it's an R value, and okay, so now with this std move thing, right, you see that the std move on L value is technically an R value by definition, right? We define std move that way, but it still maintains some characteristics of the L value. And what the characteristic, namely as a location, it still maintains that characteristic of the L value. So that's why we need to define new value categories. And so the way they define it is by doing this tree here. So now, this tree is actually kind of makes sense if you think about it, right? So the new value category that you invented, honestly speaking, all this fancy thing, the only thing that's really new is X value, right? So previously we had an L value, we had R value previously. The only thing that really introduced is X value, right? But for completeness, they kind of needed to say, for completeness, they kind of needed to complete this tree. And so now GL, the way they define it is that so previously the expression is either L value or R value, right? So in C++11 we kind of threw something in between, like previously it's L and R, then with C++11 we introduced X value here, and so they kind of need to fill up these guys over here, right? So the way they did it is they push down the L value here, and then they created a notion called the PR value. So the way they just define it is, so you look at the definitions. So these are the original value categories, and okay, so I'll just show you the definitions. Okay, so yeah, so now a GL value is something that has an identity, it's a kind of like a location. And then R value is something that can be moved. And so now if you take the intersection of all these properties, right? Yeah, you can read from the chart that an L value is something that cannot be moved, but it's an identity. Then an X value is something that has an identity and can be moved. And then PR value is something that has no identity but can be moved. Right? So under this new scheme, the full definition is here. This from directly from the C++ reference. And yeah, so let's go through each of these one by one. So the GL value is an expression whose evaluation determines the identity. So in this case, it corresponds to this over here. And yeah, basically a GL value is the original notion of the L value. Right? It's the original notion of L value, just that now we've renamed it. Then the PR value is the okay, they define sorry. A PR value is something that is a temporary basically. I like to think of a PR value as a temporary. So in this case, a PR value can be if you use something like new, right? You see it can be something a PR value, something that's created using new is a PR value. So you do like new cow is technically a PR value. Then the X value is something that is a GL value that whose resources can be reused. And basically this, for all practical purposes, an X value is something that comes out of std move. If you call std move on something, it creates an X value. Right?
So it's like a intersection value of that. It's like a transition.
Yeah.
Why is new call a PR value? Like isn't like when you run new something, like isn't that like creating like memory on the heap and then you have like some pointer to it?
No, but there's no owners of this new cow, right?
But I get what he means. He said that it's a why is the new cow considered a PR value? Okay, I think that intuition that's a good question. I don't have good answer for that, but right now I guess my answer for now would just be that the spec defines a PR value as such. So maybe instead of thinking of why a new something is a PR value, I need to rethink about my understanding of L value. Yeah, so I don't really know answer to that, but I'll be thinking about it. Yeah. So an X value is something that basically X value is basically almost always something that most of the time it's just something that when you call std move from it, it gives you an X value. And then the remaining two, L value and R value, is defined based on the more specific ones. So in this case, an L value is something that is a GL value that's not X value, right here. And then R value is something that is either X value or PR value. Okay, so that brings us to copy and move. So we saw that this reference type tells the function that it can take ownership of the parameter. So when the function can take ownership of the parameter, function or method lah. If it can take ownership of the parameter, then essentially that's if you want to define what we call a move constructor of a class or move assignment of a class, that's what you use, right? Because this is precisely the thing that tells the function you can move me. So that's why we use it for the move constructor and assignment. And for the const ampersand, it's something that cannot, it const ampersand, the reference type over there, the function cannot modify it. And so it leads itself naturally to, and you see it binds to everything. Right? So it lends naturally itself to something that is used to define your copy constructors and assignments. So this is what copy constructors and assignments look like. So in this case, the first one over here is copy constructor, right? So you can browse the link over here. I define my own class called my vector. In this case, the first one is a constructor that constructs a vector from another vector called other, right? So if I pass you a constant reference to another vector called other, then in this constructor, I can use the contents of other to construct my own vector, and this is what we call the copy constructor. Then over here is called what we call the move constructor. If I want to move from other and create a vector from that moved value. So this is we have no except here because something related to abstractions disrupting when your vector of elements, and I won't go into too much detail, but this no except is important for optimizations. Then we have this is called a copy assignment. Yeah, this is called a copy assignment, and this last one is called a move assignment. So why do we need these custom constructors and assignments in the first place? The typical example is if let's say I have a vector, as Sean mentioned, I have a vector and to implement a vector I must have a must have a pointer to int called data, right? So let's say I create a vector with size 3, int star will point in the constructor over here we see that we allocate a new array of size 3, and in this case int star data points to that array in the heap. So what if we do not have our own custom copy constructors, right? What might happen is that when I make a copy of vector v, when I make a copy of it, naively the default copy constructor, all it does is it copies each of the field value by value. So meaning that when it copies the pointer by value, it literally copies the address over to the new vector, and it copies the size over also. So in this case, you see there's a problem because if I have two pointers pointing to the same region in memory, right, then in some sense, both of these vectors, they have reference to that chunk of memory, and that leads to a problem when I free both of them. So later on, when I call a destructor on one of them, right, it leads to a double free, because what a destructor looks like is something like that, right? It deletes the data. Basically, this is a free. It frees the memory. So if I delete one of them, I delete the first vector, it frees that memory. And then there's a problem because now when I try to delete the second one, I leave to double free, and double free is bad, right? So you see that without the copy constructor, without a custom copy constructor, we end up having a double free error because this in pointer data is naively just copied over as a pointer, and both of the pointers point to the same region in memory. So that's why I need to define this thing called copy constructor, where now we see that in the copy constructor, the data is, I allocate a new chunk of memory for it, right? And then I do std copy to copy each element by element. And so now that fixes it, because now when I create a copy of the vector v, it actually allocates a new chunk of memory, a new area of memory on the heap, like this. And now when I call delete, and now I call delete, right? Each one of them will free their own respective resource. So in this case, you see that in defining copy constructor helps fix the problem of double free. And for the move constructor, it's similar. Let's say I want to define, let's say I want to move this vector into a new vector, right? Naively what will happen is I do something like that. Okay, but what the move constructor allows you to do is that, you see, I set data to equals to other data, right? This initializer listing data is other data. This essentially says data equals to other data. And after that, I actually set other data to equals to null pointer, which means that when I do a move from vector v to a move vector w, I set this equals to this original value, right? And then after that, I set this one to null. So essentially the arrow moves from this guy to the other guy, right? The arrow moves from this vector v to the other one. So now after the move operation, this data is a null pointer, and this points to where that pointed to previously. So we say that the ownership of, in some sense, the move constructor, the custom move constructor over here, transfer ownership of the data from transfer ownership of this array allocated from that vector to this vector, right? Because this arrow is kind of like a ownership. So now, so now the ownership of the resource, in this case, the resource refers to the array, is moved from V to W, right? And it's allowed because that's precisely what we said, right? We said that when I have this, my vector ampersand, remember what the R value reference type means? The R value reference type here means that this function, this method, in this case the constructor, this constructor can take ownership of other. And in this case, when the new vector being created takes ownership of other, it means that the new vector takes ownership of all the other's resources, right? Because other previously owned some chunk of memory, and now when I move other into this one, this new vector is being created takes ownership of other, and in so doing, it kind of robs the other of its resources. And it robs the other of its resources and then sets the other dot data equals to null pointer. So now the other vector has no ownership of the resource anymore. I've robbed the move constructor is essentially allowing the new vector to rob the old vector of its resources, to steal its resources. Okay, so that leads us to rule of three. Whenever you define the rule of three says that in general, more often than not, when we define when a class has a user defined destructor or a copy constructor or a copy assignment, most likely it requires all three. And the reason is simple. The reason is just that if you need a destructor, chances are that your class manually manages some resource, right? It manually allocates some resource, manually destroys some resource. Right? So it has ownership of some resource that is freed manually. And if something is done manually, when you make a copy of this class, make a copy of this object, right? You need to duplicate the resource. If not, you end up having both by default, you end up having both objects pointing to the same resource, and they both own the same resource, and then that leads to double free later on. So that's the rule of thumb. So rule of three is just that if you define any one of these, you can't, these three kind of come as a package together. Rule of five is similar, but it says that if you define move semantics, then you can't need to define all of them. So if you define the move assignment, then you need to define all five of them, I believe. Yeah. So that's because if you define the presence of user defined destructors, copy constructor, or copy assignment, it prevents implicit definition of the move stuff. So if you want custom move semantics, right? If you want a thing to be movable and you define how it's copyable, then you need to kind of indicate how it should be moved also. So yeah, so I think if you define the copy constructor and copy assignment, it by default it deletes the move, I believe. So C++ gives you a lot of flexibility, but you must be careful not to do wrong things, right? So in this case, let's say I have a function called borrow. It borrows a cat, right? Realize it borrows a cat. And then in this case, I try to create a new cat from a move constructor by doing it this way. This actually, C++ doesn't stop you from doing this, but it's a very bad practice because in this case, the person passing in the cat, it let this function borrow it. But then this function, what it did instead is it stole ownership of the cat. It's like I let the function borrow my cat, and then the function steal my cat, right? So that's bad. Yeah, so that's bad. So only the owner of an object should move it. And so if there's a double ampersand here, that'd be okay. But if a single ampersand, it indicates that the function should only borrow the cat, not take ownership of the cat. So yeah, that brings us to C++ 17 features. Now this part of the slides is not very well, it's not very well, I didn't put so much time into all that. So I'll just go through it quite quickly. Something called temporary materialization happens when basically you have an expression like cat C equals to create cat, and create cat, this create cat, that the value category of create cat is a PR value, right? Because it's a temporary. In this case, if you want to create a cat using a PR value, you need to convert this PR value into an X value. So the reason is because if we go back all the way to the tree over here, you go back all the way to the tree over here. If I give you remember that if I give a PR value, when you convert it to, if I give you a PR value but you need a GL value, right? Then you convert it to X value, and that still allows you to bind to R value references. So it still calls the appropriate function, but at the same time, the temporary in this case, which is the PR value, has materialized into something that kind of has identity. So that's temporary materialization. I don't know. Yeah, I wouldn't say I wouldn't go too much into detail here. Won't say too much, but basically this is what happens when you convert implicitly between value categories.
You have a lot of slides there.
No.
Yeah, it was-
Sure.
Like this one is great, but like sorry, I need to
Sure. So PR
That could be like 130 you catch.
No, the last one you have
Maybe fine, just sing a
Yeah.
You
right?
can just hold it. No! You come over there, not to the US, but okay, sorry. Oh yeah, I did check, but I'm still down from the.
Okay, so PR values are kind of like the interpretation of temporary materialization is that PR values are kind of like ghosts, which only become real when the real object only become a real object when it's needed. And you can read up about here, but basically basically they're saying that t variable equals to t like that is equivalent to t var like that. This block is not bad. Yeah.
You said the heat that open like a new cow, so yeah, right.
Yeah, so there's a PR value. So if you just have new cow, it remains a PR value. But if you say like cow C equals to new cow, then that new cow will be materialized into an X value. And you call the constructor of cow. Right.
Wait, so
Yeah,
PR values
I don't know.
Wait, PR values don't call constructor.
Okay, I won't say too much on this part. I'm not I'm not super good at this part also.
Okay.
Okay, so
But I'm very confused on how all this stuff helps you optimize code though.
so if like let's say I want to
Do you remember what happened?
let's say I want to pass a function into a resource. I want to pass a resource into a function, right?
Right.
So if you don't do it correctly, you do a copy of the resource. So imagine the resource is like one big vector. And imagine the one big vector, right? But imagine the function just want to sum up the elements. You make a copy of the huge vector is a waste.
Right.
So you pass a reference in that sense. So or let's say you want to transfer the ownership of vector from one guy from A to B.
Right.
Then if you do it badly, you make a copy of it.
Okay, so what instance do I want to transfer to optimize?
So if you want if you do not need if you want to transfer ownership of a vector from A to B, then instead of making a copy and then destroying one of them, you move it instead.
If I want to make a transfer A to B.
Yeah, let's say I have a vector
Okay.
that belongs to A,
Okay.
right? And I will transfer this vector to B. So that A no longer has it because I don't need A anymore for some reason. And B has it after that. So if I want to transfer this ownership of the vector from A to B,
Right.
instead of the naive way would just be to make a copy of the vector.
Yeah, then delete A, right?
Yeah. But the copy is expensive, right? So instead I can transfer the ownership by calling like std move of the vector
Okay, I get it.
and pass it over.
Wait, would that be the same as like calling std swap?
Not okay. In some sense, moving is like swapping the pointers, right?
Yes.
Imagine the pointers A and B have pointers to some vector,
Right.
where B's one is like null, right? Because it doesn't have a vector yet. Then in some sense you are swapping the vectors. Yeah, they're swapping the pointers.
Yeah.
So yeah, under the hood, the move constructor, in the move assignment, the move constructor, you are doing a swap of the pointers essentially. Yeah. So yeah, basically it's swapping pointers instead of swapping the actual vectors. Yeah. So yeah, every problem in CS can be solved with one extra level indirection, right? So okay, so
Makes sense.
temporary materialization is basically in the new spec, it's basically saying it allows you to create factories for non-movable objects. I think in the interest of time I won't elaborate more. Copy elision, you can set through this program yourself. But basically over here, if we look at this program naively, we might expect that it'll create a cat here. It'll create a cat. You might expect that over here it might create it might call the move constructor of the cat, and then over here we might expect that it calls the move constructor of the cat again. But in reality, what happens is it only calls the constructor once, and this is including the case where I actually use the cat in the function. So essentially, copy elision is an optimization that the compiler can do to avoid many copies or many moves. And previously, before C++17, copy elision was something that most compilers already did by themselves. But C++17 made it such that the copy elision is guaranteed. So they put in place a bunch of rules that say like, if you have this scenario, then copy elision is guaranteed. And the reason for wanting to do so is that if you reduce less copies and moves mostly the copies, but if you reduce less copies, then if you have less copies, then it's better for runtime, right? And basically elision means omission, so you avoid copying. That's what this means. Yeah, there's some nice animations here I won't go through, but you need to make sure that with C++17 guaranteed copy elision, you need to make sure that your program has some guarantees, like your move constructor must follow certain rules. If not, you break certain if not, your program will not be well defined. Yeah. I think universal references, I don't really have keep going.
Oh shit. Sorry.
It's okay. Universal references, I think it's okay. I would probably just stop
How
here.
about you do another talk next week?
Honestly, yeah. Your part two.
Yeah. I think
Like a little teaser for the podcast.
I don't really have
I think instead of a lot of content, like
Yeah.
no, it's
There's a lot of stuff I want to discuss. Like about,
sure. We can discuss it more.
Yeah. Yes.
Oh, yeah.
Oh yes.
Thanks a lot.